today, give you a little outline, is start section 5.2. 5.2 is going to be about types of energy. Quiet, guys, please. Specifically, we're going to talk about kinetic and potential energies. Today, we're really only going to look into kinetic energy. Okay? Kinetic energy. Now, some people in here I know have taken physical science, some have not. So I'm going to make believe we're starting from the beginning. But for those of us that have taken physical science, what is kinetic energy, or what do you think about when you hear kinetic energy? Green. Movement. Very good. Movement. So right away, kinetic, think you have to be moving. Okay? So an object has to have some velocity. And look at the equation. 1/2 mass times velocity squared. So if there's zero velocity, there is zero kinetic energy. Again, kinetic energy has to have two things. It has to have a mass. The object needs to have mass. If it doesn't have mass, it doesn't exist. And it must have a velocity. If it doesn't have velocity, for example, this pencil on my table right now, and this desk right here, has no kinetic energy. But your hand is exerting kinetic energy, or you're doing work in the form of kinetic energy. You're moving your pencil back and forth with some velocity. So movement means kinetic energy. Remember that, okay? Now, what were the units of work from section 5.1? Tristan. Joules. Same thing here. Units of energy and work are the same. They're units of joules. So let's write that down, please. Okay, our units are joules here. Our units are joules. Same thing as section 5.1.
What is that? Mass times
V squared.
velocity?
Velocity squared. Velocity squared. Kinetic energy always has to do with an object's motion. If it is not moving, it doesn't have kinetic energy. Okay? It's like, remember, force of friction kinetic versus force of friction static? Kinetic friction was when it was moving, right? Kinetic energy is moving. Potential energy we're going to hear about in the next class or two has to do with objects that are not moving, or stationary objects. Okay? Objects that might be like this object sitting on a table. It's got the potential to fall, so it has what we call potential energy, but we're going to talk more about that later. So really what we're going to talk about today is kinetic energy. All right. Now, with that said, let's take a look at our first example for today. Imagine we have a 12-kilogram bowling ball, and it moves at a velocity of 3 meters per second. How fast must a 4.5 gram, not kilogram, but gram, 4.5 gram bouncy ball travel for it to have the same amount of kinetic energy as the bowling ball? So you know those bouncy balls, are they called super balls, really? Or you bounce
High bouncy pinkies?
Were they? High bouncy balls?
Yeah, you get them over here. They're the greatest. They're like the pink ones that bounce really
Oh,
high.
I haven't seen
No,
those.
they're
all
called-
colors.
No, they're called high bouncy
All right,
pinkies.
relax. Now,
Helen.
we want to know
My
at
dog
what,
ate it and threw up.
at what velocity must the Super Bowl travel so that it has the same kinetic energy as a bowling ball? Before we get into this example at all, think about something that makes maybe even more sense than this. If you have a linebacker in football, okay? Big linebacker, make believe he's like 320 pounds, big guy. And he's running to tackle someone who's a running back. And the running back is a small running back like Barry Sanders. You know, anybody know who Barry Sanders was?
Oh, yeah.
Okay, short guy, really good movement,
Yeah.
good lateral movement. So, imagine Barry Sanders is running against the linebacker. The linebacker's running, and he weighs 320 pounds, but Barry Sanders only weighs like 200 pounds, a small guy. For him to overcome the linebacker, either he's got to beat him, like he's actually got to run around him, but to actually like barrel through him, he needs to run faster, right? So he has more energy in a sense. So right away for this problem, for a bowling ball to have the same energy as a bouncy ball, that bouncy ball has got to be going pretty fast, right? Because the bowling ball is so massive that naturally it's got a lot of energy. It's got a lot of inertia to it, got a lot of mass. So for this problem, our answer should be something larger than 3. At least it better be something larger than 3. We would hope it's something larger than 3. Because the bowling ball is moving at 3 meters per second, the bouncy ball has got to be moving faster than that to compensate because its mass is much less. Its mass is only 4.5 grams, whereas this is 12 kilograms. Okay? Chaz, want to start us off?
Yeah.
So what do we know?
I don't know if this is right, but well, first, you know the mass of the bowling ball, so you put 12, and velocity.
meters per second.
Got it.
All right. Keep going.
And then you have the mass as a bouncy ball, which is 4.5 grams.
Convert it.
Altogether grams, you do
Yeah.
over 1 over 100.
0.45.
1,000.
1 over 1,000.
So 1,000 is how many zeros?
0.045.
3 zeros.
So move it over.
0.045.
Close, close.
0, 0.
0,045.
And that's kilograms.
That's our mass of the bouncy ball. And what are we trying to find?
The kinetic energy.
No, actually we're not. We're trying to find.
Oh, sorry, the velocity.
You okay? You sure?
Really embarrassing. So weird.
You're trying to find the velocity. So what I was going to do, I don't know if this is right, because we have all the information for the bowling ball. I was going to plug that in. And
Fine.
And find the kinetic energy.
Good.
And then you can sub in the information of
Good.
the bounce ball and solve.
Alright, so what Shanna said is exactly right. Some of us might not be able to hear it if we don't stop talking. The kinetic energy of each of these needs to be the same. So you can start by finding the kinetic energy of the bowling ball, set it equal to that of the Super Bowl. Because the problem says, how fast must it be traveling for it to have the same kinetic energy? Okay? This problem here, we're looking at an object that's just moving at a speed of 3 meters per second. That's if we have an object dropped or vertically moving when it's negative 9.81. Remember though, our formula is only 1/2 mv squared. Kinetic energy has nothing to do with the acceleration, really. You can have a change in kinetic energy, but we're not talking about that just yet. So what I would do is this, to make it even easier. I would say, yeah, you're going to find the kinetic energy of each and set it equal, so just say this. That's what we're saying, really. KE1 equals KE2. The kinetic energy of the bowling ball must equal the kinetic energy of the bouncy ball.
Okay, yeah.
Okay? Which is what you said. But you would do it, you said find this first and then set it equal. I'm just going to say let's set it equal to start.
Okay, cool.
Now, beyond that, after this, we need to, come on, scroll. All right. What we need to do next is write our formulas. For the kinetic energy of the first object, it's again 1/2 mv squared. I'm going to use subscripts to indicate it's the first object here. For the second object, it's also 1/2 mv squared, but it's the second object. So I'm going to use subscripts of 2 for the second object. Again, the subscripts are only identifiers. They are not powers. So this is squared for velocity, but the 1 and the 2 in the subscript just indicates the first or the second object. There's a 1/2 on both sides. What can I do? Yeah, or just, if I multiply by 2, what happens on both sides? They cancel. So get rid of the 1/2 on both sides. It's multiplying both sides by 2, getting rid of it. So I've got m1 v1 squared equals m2 v2 squared. Okay, so far? Again, this side of the equation here is the bowling ball. This side of the equation is the bouncy ball. Now, we want to figure out v2, the velocity of the bouncy ball. So I need to isolate the variable v2. So I got to get rid of that m2 first. How do I get rid of that m2 in front of it? Divide. So let's write this over m2 and divide by m2. We're going to see on this side, we have m1 v1 squared over m2. These m2's cancel. This equals v2 squared.
Wait, why divide by m2?
What are we solving for? We're trying to find the velocity of the bouncy ball, which is v2 right here. So you want to get v2 by itself. Since m2 is multiplying, we divide by m2. Again, remember people, what am I doing? I'm solving for the general solution. If you want to plug in numbers at this point in time right here, or even up here, you want to plug in numbers, be my guest. You can do that. It makes it easier for you. Okay? That's not a problem. Now, I want to get rid of the square. So what do I do to both sides? Square root. Square root, not square the whole thing, square root. Okay, be careful. So take the square root of both sides. for this problem here, we want to get v2 by itself. We've done that by taking the square root. But now you'll notice, and some people get confused here, v1 is still squared. You don't just drop that square for no reason. Okay, this whole thing is in the square root. You can leave it like this and plug in your numbers now and see what you get. You could also simplify this further by taking the v1 outside and get rid of the square. But you don't have to do that, so don't worry about it. Just plug in your three numbers here. You know the mass of the bowling ball is 12. You know the velocity of the bowling ball was, what was the velocity? 3. So 3 squared, all over 0.0045. Square root that answer, you'll get the velocity of the super ball or the bouncy ball, whatever.
Did you have to do the square root in this problem?
Again, you're going to at the end, but if you plug in numbers here, you get this number equals v2 squared. Then you might have a number here, then you got to take the square root.
So what if, like, for KE2?
For what? KE2?
Yeah. If I just did it separate, like, instead of equal to each other?
You did KE1 over here, got a number. You did KE2, wrote it as 1/2 n times v squared, and then you set them equal?
Yeah, that's what
You got to set it equal either way, because it says they have the same kinetic energy. So whether you do them separately or together, in the end, they got to do together anyway. Okay? So, for this problem, let's plug in. We have, again, it's going to be the plus or minus the square root of 12 times 3 squared over 0.0045. This should give us an answer. Check your numbers, please. Of 154.9.
Yeah.
Okay, please check your answer. Don't just assume I'm right. I want you to do this yourself as well. What are my units of velocity? Good, meters per second. Okay, meters per second. So did joules even come up in this problem? You know why they didn't come up? Because in the beginning, we set the energies equal to each other. We said KE1 equals KE2. And then we went ahead and solved. Had you had solved for KE1 in the beginning, you would have an answer in joules. Then you have to set that equal to KE2 and then resolve for V. It's the same thing, really. Why you would...
Why you would still put it in joules? Like if there was like a problem that involved using K, I would just automatically put it in joules.
Because if the problem said find the kinetic energy, it's joules, the answer. But this problem says at what speed must it go so they have the same kinetic energy. So you're now finding a velocity. You're now finding the velocity. So,
You have to get to,
Gabby, go ahead, one more time.
so you have to get KU equal to KU, which is why.
Exactly. That's why we set them equal in the beginning. The 0045 comes from the fact that the mass was given in grams.
Oh,
Okay? It needs to be converted to kilograms.
So this was like one of those 2-point questions where they, like, you know, where they ask like, first they ask like, what's the kinetic energy, and then they ask like, what's the.
Then you would do it that way.
You
Yeah.
said like, you would have filled in like, you would have found K, and then you would have set the other one to it. And then
Exactly. That's good. I like the way you think about that, Helen. Very good. If it's like the two-parter question she's asking, like ABC, you might have said find the kinetic energy, then find the velocity, then it would be like a scaffolding problem. Yes. Yes. Okay. All right. Scaffolding. Scaffolding. Next thing we're going to look at. Next thing we're going to look at is called the work kinetic energy theorem. Okay, the work kinetic energy theorem. Now, what I'd like to do is, instead of deriving it and showing all the work of where this theorem comes from, I'm going to just give you the theorem for now, and I want to get right into the example. Okay? K equals 1 half mv squared, the last equation is a theorem. I mean, just a theorem. Okay? The theorem says the following. The theorem says this. The work done on an object is equal to the change in the kinetic energy of the object. This is going to relate. Nice. This is going to relate section 5.1 and 5.2. The work done on an object, the force pushed, that work done from yesterday or from the other day, is equivalent to the change in the object's kinetic energy. Okay, the change in the kinetic energy. So the way I write this is as follows. What does the F and the I stand for again? Final and initial, very good. So here we can write this as even further as this. Okay? Again, kinetic energy is 1/2 mv squared, but if we're looking for the final kinetic energy, we use the final velocity. If we're looking for the initial kinetic energy, we look for the initial, or we use the initial velocity. W is work. Remember from last section? You said you did the homework and there weren't problems on it. You remember?
I never said I did the homework.
Yeah.
That's what work is defined as. You should probably do that homework. Now, what we're thinking about today is the idea that if I were to take this chair right here, it's a very concrete example of what I'm talking about here. If I perform some sort of work on this chair by pushing it, right? I'm going to push this chair and do work by pushing with a force over a distance. Now, it's going to slide all the way over the step. What did I do? I gave it some velocity, didn't I? I gave it some motion. So really, what I gave it was kinetic energy. The work that I performed by pushing resulted in motion. It resulted in kinetic energy. That's what this theorem says. Any work that you perform will have some sort of a result in the kinetic energy change. So what's the kinetic energy of the chair right now?
0.
Once I start moving it, it's got some value, right?
Yes.
The amount of kinetic energy that it's going to get is equivalent to the amount of work I do. It's kind of an amazing theorem to think about. It happens to be identical. So if you perform like 150,000 joules of work, that's how much energy the object will gain in kinetic form. Okay, the work kinetic energy theorem.
In like theory, I guess, like what's the relation between like work and force? Don't they kind of seem like the same thing?
Yeah, okay, these are great questions. The answer to that, I'll give you a general answer because the answer is in calculus. It's called the integral. The work done is the integral of the force. It's a term in calculus. Here's what it means really. It means that if you know,
Your boxes are cages.
thank you, if you know how much work is being done over a certain distance, okay,
Yeah.
or let's say for now, let's say you know how much force is being done. If you know how much force is being pushed over a certain distance, and that force, say that force increases, then it remains the same, then the force decreases, then the same, then drops down automatically. The area underneath this curve, see this area here,
Yeah.
is the work done. They are related to each other. And that comes about from this formula right up here.
Yeah. Well, you could like see it there, but when you're like talking about it, they kind of seem like they're the same thing.
They kind of, yeah. The work done is a result of the force.
Okay.
So force is work is a function of force. In calculus, we would write it like this. Work is a function of the force being applied, and that is equal to the integral of that force with respect to its distance. But it's just the terminology, that's how they're related to each other, which is what this equation says without actually using any calculus involved.
Is that like because you push the chair and like the force is only right at the initial push, but then the work is like throughout the entire?
The work is a result of the initial push, but if you had a push that continued the whole way, then the work continues also. So that initial push that I exerted for like 12 meters might have been up to like here, might have been this area here. But then I start pushing constantly, there's more work. Then I push less, there's even more work here, and then there's more work there.
Okay.
Okay? Steph.
So the cosine
Guys, quiet please,
of
listen.
the theta, that comes from the angle that you push it at?
Yes.
Okay.
Yes, that's from last class, correct. Correct. All right, so let's go into an example now. Let's go into an example. I'm telling you now, we're going to use the work kinetic energy theorem. W equals delta KE. Okay, W equals delta KE. This is what you will be given on your test as a formula. You're going to be given literally this right here.
We'll have to break that.
Okay? Well, you also will be given kinetic energy on the side. You'll be given kinetic energy equals 1/2 mv squared. So by definition, you should be able to plug this in. Okay?
Okay, but you broke that down into final and initial. I don't understand why you did that.
Because, let's go through the problem and you'll see. How about that? Make it easier. Okay? So, on a wood floor, you decide to slide around when you just put on a new pair of socks. I did this the other day, and that's why I thought it was a problem. I got a new pair of socks the other day.
Sliding around.
And I was downstairs, and I was like walking downstairs, and I slid a little bit too far. And I thought of this when I was doing that, so I made
Did
this
you just
problem.
see him like running in his house
And then
and
he's
like
like,
sliding?
and then he's like, this is cold.
A lot of your problems come up like when like things happen to me, you think of it.
Wait, you live in a brownstone?
I don't even know where Brownstone
No, he lives in his grandma's house.
Now,
Grandpa.
your people,
Grandma.
can we focus on
He's
that?
just fixing the house up.
Now,
Grandpa.
your mass is 50 kilograms. So your 50 kilograms, your actual mass, and you run and you start to slide across the room. So you run and you slide with a speed of 1.5 meters per second. Now,
So be adult.
after that, stop, focus. You run with an initial speed of 1.5 meters per second, and you start to slide. The question becomes, how far will you move? Find the distance or displacement in this problem. If the coefficient of kinetic friction between your socks and the wood floor is 0.25.
Was that you?
Okay, mu. Very good. So, we're going to use this theorem. Before I go into this theorem, let's start givens. First, what is your mass?
25, 50.
Chaz? 50. Now, besides the mass, what else do I know? Show of hands, please. Chaz, thank you.
Initial velocity is 1.5 meters per second.
You know
And what's the final velocity, Chaz?
Zero.
Why is that the final
Velocity. It's zero because you're gonna stop.
Good. Good. It's 0 because you're going to stop. So, you're running across the room, you start sliding, and then you come to stop, or you come to rest. So your final velocity must be 0 here. It must. Okay?
And your UK would be 0.25
Good. UK is 0.25.
because
It says coefficient of kinetic friction.
So kinetic friction is the
no, it's different.
Friction.
UK and US are different. The kinetic friction has to do with the size of the gravity and the
I know the difference after this. How about K and S?
But generally speaking, mu is just the coefficient of friction. Mu K is the coefficient of kinetic friction. Mu S is the coefficient of static friction.
So what's the equation?
That's what we have to figure out now. Okay? So let's go into this. Let's take a look. From last class, section 5.1, what was our definition of work? From 5.1, Erica.
Equals F cosine theta, the absolute value of
Green,
times-
stop. Please. I know it's not just you, and you're going to tell me that in a second, but it's always you every time. Please. Erica, go.
F equals, W equals F cosine theta times the absolute value of x.
So that's on the left-hand side of the equation. F cos theta, absolute value of x. On the right-hand side, delta KE means KE final minus KE initial. Before I start writing equations out, think logically, people. The object comes to rest, doesn't it?
Yes.
Does it have any kinetic energy then? At the end?
No.
But initially it does, right?
Yeah.
Why?
Because you're moving.
It's in motion. Object is in motion. It's initially in motion, so there is KEI, but there is no KEF in this problem. I'm still going to write it out to show you that, but I want you to see that before you even start the problem. Okay? So I'm going to move these over real quick. Hold on. Hopefully, no. Maybe so. Alright. So we're going to have set this equal to KEF minus KEI. That's what you're always going to start with. Okay? You're always going to start with final minus initial kinetic energies. Next, start plugging your equations, or start plugging your equations here. You've got 1/2 mvf squared minus 1/2 mvi squared. Over here, what force, and this is the thing that's tough to figure out here, what force is causing you to stop? Friction. So instead of F, let's call this FF, please, to specify that we're talking about our friction force here. FF.
Why is the value of W equal to KEF minus AEI?
Because that's the theorem we started with?
Oh no, I mean like that's like the F cosine theta.
This is work from the last section. That was last night's homework.
Yeah, I
So
know.
we're replacing work with that. We're replacing delta KE with that. I'm just moving down the line, okay? Now, if I'm sliding across the room, if I'm sliding this way, which way is friction acting?
That way.
So what kind of an angle does this make up?
180.
180 degrees, right? 180 degrees, that's the angle that's made up here. So already we're going to know that we're going to do the cosine of 180, and we're going to be trying to find x. How do I know I'm trying to find x in this problem?
Wants to know how far.
How far, which is x. Very good. Very good. So here, we can still write cos theta and put a little x there. Now, everybody go like this, please. There is no final velocity. This value is 0. So draw your line through it and make this whole thing go to 0. Okay? And again, it's only this portion that is 0 in this problem. Okay? There is initial velocity.
Are these on our problem sets, or is that just all chapter?
This is going to be on your problem set number 5, not for a little while. Problem set 4, which you're going to work on a little bit of tomorrow, and then actually on Friday when I'm not here, that is on section 4.4, the video that you guys will watch on inclined planes.
All right, cool.
Okay? By all of you, I mean the 21 that I watched. Whoever the 14 are, better get on there. Okay?
I watched.
21 people have watched section 4.4 still, and this has been about a week and a half
Does it
now.
show who?
It's kind of sad. It can show that, yes.
Did you see that I watched it?
I'm not going to go into it. Let's just say that 14 people haven't. Now, at this point in time, we're trying to find the value of x. So just get rid of everything that's not x on this side. How do I get rid of this stuff if it's multiplying? Divide. So divide by f cos theta. Divide by f.
Wait, do you think it's easier to do it that way or just fill it in and then?
I think it's easier to do this.
Personally, I've always done it this way, and it's more powerful of an answer because what if I give you the same exact problem, right? And say, now the mass is not 50, the mass is 75. All you got to do is change in one variable. That's it.
Yeah.
Instead of plugging in everything in the beginning and resolving, all you got to do is go look at your final answer, and instead of putting 50 in front, you can make it 75, or you can make it 100. So you're solving for a generic solution, so it's a function of the variables. It's very powerful, it's a term. So this cancels with this. We're left with okay, that's our solution right now for the displacement or for the distance traveled by this object once it starts to come to rest. Now, the problem is this. Let's take a look at what we've got, people. I'm going to point. You tell me yes or no whether we know the value. Yes or no?
Yes.
Yes. What is the mass?
50.
1.5. 3.
0. 180.
We do know that's 180, but do we know this?
Wait, yes, you.
We know mu. We don't know FF, but we do know from last chapter, from section 4.4 again, we know that the force of friction equals mu Fn. So replace this FF with mu Fn.
There's a lot of replacing going on.
There is a whole lot of
I
stuff
remember
going
you
on.
saying
Chess.
this gets easier.
Is theta always going to be 180 for these problems, or is that a given?
Well, it's a given in this problem because it's friction, and friction opposes motion. So the angle of the motion and the friction force is 180.
So it's always going to be flat. All right.
Yeah, it's a flat surface. Okay. So, we've got, here's how I want you to write it now, please. Please write it like this. Negative mvi squared over 2 mu fn cos theta. Listen before you all make noises. Mu fn, right here, mu fn replaces the force of friction. Again, mu fn is force of friction. That's our definition.
Wait, why'd you
And
make it
instead of putting a negative 1/2 up top, I moved the 2 down to the bottom, which you can do. It's a fraction. I just took this 2 and put it down here as a 2. And I left the negative 1 up top. Okay, that's why this is negative.
Why was it negative to begin with?
Because look at your formula. Go back.
This is hard because you choose
Oh, because it's negative 1/2.
minus, it's F minus initial. Remember, KE final minus KE initial?
Yeah.
Alright? Now, here's the next issue we run into. Here's the next issue.
You don't know that.
Yeah. What do we know about FM? We actually do. We have
Yeah.
to talk about this now. We don't know it right away, but we're going to have to replace it with something else. So let's think about this as a free body diagram. If I have gravity acting down, and I have the normal force acting up, and this object, you, the person, is only sliding left to right, that means that in the vertical direction, aren't they balanced?
Yeah.
It equals what? Yeah, so we have, in the vertical direction, Fn minus Fg equals 0. So Fn is really just what? Positive.
Yeah, but wouldn't it be?
Add it.
Oh, yeah, there it is.
Okay. Alright, so Fn and Fg, the normal force, here's your key to remember, by the way. Whenever there's only horizontal motion and the ground is flat, the normal force and the force of gravity, right here, are always equivalent. Again, if there's horizontal motion only, and the floor or the surface is flat, it's not an incline. Incline is different. Then these are always balanced. And remember that Fg, the weight of any person or object, is defined as mass times 9.81. So we can write Fn is really just mg. So we're going to take this now and plug it in there for Fn. Okay? So there's a lot going on for this kind of problem. You're going to notice right away. Well, I'm going to make her write it 6 more times. Nice guy. So, what we notice now is what's in both the numerator and the denominator? M. Everybody see that? The mass?
Yeah.
There's a lot of replacements.
There's a lot of replacement, but notice the mass is here,
Mass times mass.
and the mass is up here as well. It's not, it's mu. Come on,
But
it's mu.
that's negative, so you can still
Mu,
cross,
mu,
you
mu.
can cross it out anyway. You got
Sure, you leave the negative behind, but you can cancel the factors. It'd be like saying you have negative 7 over 7, it results in negative 1. You can cancel the 7, but you got to leave the negative behind.
Yeah, but I don't think that makes it easier at all. I think it's easier just to find the Fn.
Well, you know why? Guys, listen. You know why it's really important to do it this way? What if the problem didn't give you the mass? You don't need the mass to solve. But if you did it the other way and plugged in numbers, wouldn't you have had to plug in the mass earlier? Think about it. If you found the kinetic energies earlier and you plugged in at the beginning of the problem, you would have to plug into 1/2 mv squared, and you would have needed the mass. But it turns out that the mass is not even part of this problem. So you might be given a problem on the test where it asks you to find the distance traveled for like this without giving the
Yeah,
mass.
but why do you have to write it? Like, why can't you just leave it like friction force, find the friction force, and then plug that in?
Because the friction force is mu Fn, which is mu mg. But if you don't know mass, you can't do that. You can't find the friction
There's no
force.
mass, so.
Hypothetically speaking,
What is
mu was given in this problem. It was like 0.25 or something.
Yeah, oh, it's 5, yeah.
So cancel your masses. So x turns out to be,
Your box fell.
when you cancel the x's,
Don't you use boxy things to clean clothes?
when you cancel the masses, you get
The absolute value of x equals negative e I squared over 2 mu times cosine theta.
Wait, so. Mr. House,
yes,
you canceled out that because.
because they're in the top and the bottom.
Oh,
Just like if you had x over x, they reduce, right? So that's what your answer turns out to be. If you say you have this problem on the test, okay? And you answer, and you get this as your answer. You don't even really need to plug in numbers. If you wrote all this work and got that answer, that's completely right. I can care less what the numbers are once you plug them in.
Oh, really?
The fact that you know how to go through the problem and come up with a solution. Now,
That doesn't sound like physics.
if you're an engineer and you study this for life, and you have to actually give real answers, then the numbers do matter, obviously. You want to know what the distance is. But
So
theoretically,
we never have to use numbers from now on?
if you can get to this point and you're able to do this in your test, I don't have a problem at all. You don't need numbers at all. Okay? But if you did plug in numbers and you wanted to see what you ended up getting, you get around 1/2 meter. 0.46 meters. Again, what am I plugging in? Remember, theta is 180. G is 9.81. Mu is a quarter. VI is 1.5. Well, the mass was 50, but I didn't plug it in because it doesn't matter. This problem, the masses end up canceling, so the distance traveled is not a function of the object's mass. So that says pretty much this. If I ran across the floor and did that, or if a 2-year-old ran across the floor and did that, and they were this big, then we would go the same distance if we actually did this, which is kind of amazing to think about. You would think about the fact that a heavier person would affect it. Turns out it wouldn't. If a heavier person can get up to 1.5 meters per second, and so is a lighter person, they're going to travel the same distance, because mass has no effect on the problem. So below that error. It was given in the beginning of the problem. It said the coefficient of kinetic friction between your socks and the wood floor is 0.25. And that was the actual statement in the problem. Erica.
It does gravity still say negative, yeah, right?
Does gravity still say
It's still
negative?
negative 9.8.
No, it's positive.
It's positive?
Because remember,
But then how do you get a positive answer because you're dividing by
It's
negative?
the square. It's
cosine 180 is negative 1.
What's G?
Wait, what?
This-
Okay.
Type in cos 180. Cos 180 is negative 1.
Why isn't it negative then?
Because remember, the reason we ignore the negative, Erica, when we
It's
look
the
at
absolute
forces, no, not the absolute value. The reason we ignore the negative, Erica, is not the absolute value. It has to do with our vectors here. When we draw a free body diagram, see how this is pointing down? It already takes into account the negative.
And maybe go back and look
Why don't you just wait? We're about done. We got done anyway.
So what's G?
Then just go. I don't want you to be in the middle. Sorry? 9.81.
He doesn't want you to pee in the middle of it.
That's about it, 9.81?
It's not negative 9.81?
Say again?
It's not negative 9.81?
No, because remember, when we look at forces, it's only negative 9.81 when we're looking at projectile motion. When we're looking at forces, we account for the negative part by using the vector for weight down. Remember, FG is down.
So for now, it's just positive.
Wait, do we have to take a midterm in this class?
Of course.
Everyone has to take it.
Um,
You can
You
exempt.
get exempt?
I don't know how exemptions work at this school.
The teacher is the teacher.
You have to have like above a 90 average.
And if you have above, like, I usually do above an A, so that'd be like a 94, but I'll come up with it, I'll let you guys know. I haven't even thought about that yet. That's way ahead. All right, so tonight, here's what you're going to do. Here's what you're going to work on tonight. Let me see if I have the homework on here.
I got 58 in my calculator.
58, I hope not.
I did.
Hang on a sec.
Wait, now that we're done, can you go get the...
All right, here's what I want you to do tonight. Take a look at these first problems here. Okay? 172, 1, 2, and 5 are problems about kinetic energy only.
I'm gonna do my homework tonight.
176 is kinetic energy work theorem. So this is kinetic energy, the first problem we did. This is kinetic energy work theorem, the second problem we just did. So these two things that are highlighted. Again, 172, let me just copy and paste that, hold on. It'll be on Moodle, it always is.
Mr. Howell, can you go through the last part of the problem we just did?
The last part.
The calculation of the answer, like I'm not getting that. Yeah, I keep getting 58.
First of all, hit your mode. Are you in radian or degree mode? In degree? You checked, right? Okay. Guys, I'll put this on Moodle. It's always on Moodle. It'll be on Moodle tonight. Because you have an agenda, so you could write it down if you want
I
to.
mean, I like to set my